Good morning, sir. Myself Aditya. In your class, TOC class 23BCE1344. Today, I'll be going to tell you about definition of algorithm in theory of computation. I'll be presenting this PPT as an assignment. So, what is theory of computation? The theory of computation is a branch of computer science that focuses on understanding the nature and limit of computations and computational powers. We will be studying about algorithms. We'll be talking about different type of algorithms, Turing machines, and all. It explores how problems can be solved using algorithms and investigates different computational models and their efficiencies. We'll be talking about these things in our PPT today. So the first question comes up is what is the importance of theory of computation? The theory of computation plays a critical role in various domains like algorithms, programming languages, and complexity theories. In algorithms, it provides a groundwork for developing algorithms that can solve complex problems efficiently. In programming languages, it influences the design and implementation of programming languages, enhancing their capability to express the algorithms. Talking about complexity theory, it assists in classifying problems based on their computational difficulty, helping to determine which problems are feasible to solve with available resources. So, what is an algorithm? An algorithm is defined as a finite sequence of well defined instructions or rules aimed at solving a specific problem or performing a task. Algorithm can be represented in multiple forms, including natural language, pseudocode, and various programming languages, depending on context of their application. So, what is the role of algorithm in computation? It's a simple question. It helps the role of algorithm in computation is it helps in systematic problem solving, data processing, and decision making. Like it provides a structured approach to solving problems by breaking them into manageable steps. Algorithms enable efficient processing and manipulation of data, essential for tasks such as data analysis and database management. Many algorithms are designed to assist in making decisions based on input data, such as machine learning applications. So, what are the characteristics of a well defined algorithm? It gives us a finiteness, unambiguity, output, and effectiveness. An algorithm must always terminate after a finite number of steps, ensuring that it doesn't run indefinitely. Finiteness. Each instruction should be clear and unambiguous, allowing for a straightforward understanding what need to be done at each step. What is the input? We also need input, right? So an algorithm can have zero or more inputs, which are values needed to execute the algorithm. Everyone must have written the code till now, so we know what input and output in an algorithm means. Output is at least one output should be produced, which is the result of algorithm execution. Effectiveness. The operations specified in algorithms should be sufficiently basic that they can be executed in finite amount of time with available resources. So there are two types of algorithm: deterministic algorithms, non-deterministic algorithms. These algorithms produce same output for a given input every time. Uh, One second. Okay, these algorithms produce the same output for a given time every time they are executed. These are deterministic algorithms. Example include simple sorting algorithms like bubble sort and mathematical computations. Non-deterministic algorithms. These algorithms may yield different type of outputs for the same inputs due to use of randomness or probabilistic methods. Example include algorithms used in optimization problems like genetic algorithms. What's the historical perspective? Alan Turing introduced the concept of Turing machine, a theoretical model that describes how algorithms function and their limits. Alonzo Church developed the lambda calculus, which provides a formal framework for expressing computation and algorithms. The Turing machine, we are going to talk about Turing machine now. The Turing machine is a theoretical device that manipulates symbols on an infinite tape according to a set of rules. It consists of a tape divided into cells, each capable of holding a symbol, a head that reads and writes symbols, and a state register that stores all the current state of machine. It serves as a model for defining algorithmic processes and helps in understanding the limitations of what can be computed. So, what's the computability of Turing machines? The computability theory, the computability theory examines which problem can be solved using algorithms. It differentiates between problems that can be algorithmically solved and those cannot be solved, often referred as undecided problems. Examples of computable functions include addition and sorting, whereas the halting problems is a classic example of undecidable problem. So, talking about complexity, complexity theory investigates how efficient a problem can be solved with algorithms. Time complexity tells us the measure of amount of time an algorithm takes to complete a function of input size, often expressed as big O notation. Just like bubble sort use O n square notations, that is big O time complexity notation. Space complexity tells it measures the amount of memory space required by an algorithm as the input size grows. There are various algorithms which take O n square space complexity to reduce the time complexity. Although we need to manage both aspects to make an algorithm efficient. There are some example algorithms like sorting algorithm like quick sort, merge sort, bubble sort, selection sort. There are various type of sorting algorithms. Search algorithms, binary search, linear search. There are efficient algorithms to find an item in a sorted list. Language recognition algorithms. Deterministic finite automaton (DFA) is used to recognize patterns within input string. There are also some limitations of algorithms. The halting problem serves as a fundamental example of an unsolvable problem. It states that no algorithm can be universally determine whether another algorithm will hold, finish running, for continue to run indefinitely. This limitation showcases that not all problems can be algorithmically solved and highlights the need of different approach in the computation. There is also a factor that plays an important role, that is decidability. Decidability problems for which there exists an algorithm that can provide a correct yes or no answer for all inputs. Example, determining if a number is even or not. Undecidable problems that cannot be solved by any algorithm, like halting problems determining if a journal algorithm will hold or not. There are some problems which can't be solved using algorithms. Decidability can assure you that every problem in the world cannot be solved using an algorithm. There are practical applications for algorithms also, like the principle of algorithm theory find applications in various fields. Compilers utilize algorithms for parsing, code generation and optimization, transforming high-level code into into machine languages. Artificial intelligence. The algorithms underpin machine learning models, enabling system to learn from data and make predictions. Cryptography. Algorithms are essential for secure communication, with cryptographic algorithms ensuring data confidentiality and integrity. So, I guess we came to the conclusion of our presentation. The theory of computation and algorithm are fundamentals to understanding the capabilities and limitations of computers. By defining clear problem solving strategies, algorithms enable efficient and systematic approaches to complex tasks across diverse fields. Through concepts like computability and complexity, we gain insights into which problem can be solved and the resources required to solve them, guiding advancement in computer science and technology. That's it, sir. Thank you for giving me the opportunity to speak in front of a presentation. That will be all from my side. Thank you.